Hi and welcome to this tutorial on chemical equilibria applied to industry. In the previous tutorial we had a look at Le Chatelier's principle and how temperature, concentration and pressure shifts an equilibrium or a system in dynamic equilibrium, and how catalysts don't affect the position of equilibrium. So here we're going to have a look at catalysts in terms of industry, so the Haber process and the contact process. You'll know from GCSE, because I'm sure you've come across the Haber process before, that there is a compromise in industrial reactions. So for most industrial reactions, we're going to want to have high temperatures, high pressures. However, the high energy demands obviously increase the costs. So they result in high costs. They might also result in safety challenges, especially with high pressure, and optical conditions often therefore have to be compromised for as well. Some reactions need a very low temperature, but that's going to affect the rate of collisions, for example. So there's just compromises all over the place. So the factors that need to be considered, we're thinking about costs, we're thinking about yield, and so shift in the equilibrium, and we're also thinking obviously about the rate of reaction as well. So if we're having a look at the Haber process here, this is a nice diagram of what's going on. Check your spec, you might need to know a lot of detail about this actual process in terms of mechanically. But a reminder of the actual process itself, we've got nitrogen gas and hydrogen gas reacting to make ammonia. Okay, and in terms of it's an exothermic reaction. So we want 82 kilojoules per mole. So if I rewrite this at the top, we can see that in order to get the maximum amount of ammonia, we need to shift the equilibrium to the right, don't we? Because that's what we want. We want this, the ammonia. So we need to shift that equilibrium over. So according to Le Chatelier's principle, the equilibrium will shift to the right at a lower temperature because the forward reaction is exothermic. Okay, so the forward reaction is exothermic. Therefore, if I lower the temperature, then it's going to want to increase the temperature and it's going to want to take the exothermic pathway, the forward pathway. So ideally, we'd have a low temperature. And we also can shift it because of pressure, because all of these are in their gaseous forms. I've got 1, 2, 3, 4 moles of gas on that side, and I've only got 2 moles of gas on the other. So therefore, if I increase the pressure, then we're also going to want to minimize that increase in pressure. We're going to want to reduce the pressure, so we're going to shift to the right where there's less moles of gas. So what we're thinking of is we want low temp, ideally, and we want high pressure. That's going to shift our equilibrium in the direction that we want. That's going to increase our yield of ammonia. Okay, but we also need to consider the rate of reaction. So we've got a danger here. Low temperature, we know, is going to reduce the rate of reaction. We've looked at the Maxwell-Boltzmann distribution. It's going to leave us with a lower proportion of molecules that have the activation energy or above. So we're going to get less successful collisions and the rate of reaction is really, really going to go down. So for that reason, we do actually need to use quite a high temperature. So we're going to use around 400 to 450 degrees Celsius as a compromise. And that's going to ensure that we still get a reasonably high yield of ammonia with the faster reaction rate. And of course, we need to consider the cost of the entire reaction. So high pressure is going to increase the yield. It's going to shift our reaction to the right. And it's also going to increase the rate because the high pressure does tend to increase the rate as well. However, using the high pressure is really expensive. It requires specialist equipment. The equipment requires a lot of maintenance in order to keep the staff safe. Okay, and for this reason, they compromise again. So we're going to compromise with 200 atmospheres of pressure, which is still high, but we could have it higher, but it's a nice compromise. So you need to remember those conditions. A summary is that we're going to use the temperature of 400 to 450 degrees Celsius. That's giving a high enough rate, but not too high. And it's not too high a temperature such that it shifts it too far to the left and we get too little yield of ammonia. So it's that compromise, and our pressure of 200 atmospheres to give a high rate and yield, but to keep the staff safe and keep the costs low. Okay, so filling in this table, we are going to maximize the rate. We need a high temperature and we need a high pressure. To maximize the yield, we need a low temperature, but of course a high pressure. That was to do the equilibrium, the Chatelier's. To get a cost, of course, we need low both. That's ideally what you would have. Let's look at the contact process then. So check your spec as to how much detail you need to know the contact process in specifically. To remind you, we've got our sulfur dioxide with our gaseous oxygen reacting to form SO3. Okay, and that forward reaction is also exothermic, so minus 197 kilojoules per mole. All right, so to get the maximum yield of sulfuric acid, we obviously need to shift our equilibrium to the right. Okay, that's the important thing we need to do. So very similar to the Haber process. And according to the Chatelier's principle, to shift to the right, again, we need the lower temperature because the forward reaction is exothermic. So if we lower the temperature, it's going to want to heat the system up to counteract the change, and it's going to want to shift to the right. So we need a low temperature, and we also need a higher pressure, because jumping back, we've got 3 moles of gas on the left-hand side and only 2 moles of gas on the right. So if you increase the pressure, we want to counteract the change by reducing the pressure. So we're going to shift to the side with the less moles, the right-hand side. So again, very similar. We're wanting a low temp, ideally, and we're wanting high pressure. Okay. So again, we've got a really, really similar thing happening here. So we're going to compromise, and we're going to compromise with the same temperature. So we're going to go 400 to 450 degrees Celsius. Okay, so that means that we've got the temperature is not so high that it shifts us completely to the left, where we don't get any yield of the sulfuric acid, but it's high enough so that we actually have a good rate of reaction. So we're actually going to get a reaction happening and a reasonable yield. And then the cost. So a high pressure, fine, but that has a cost and safety implications. We need really strong pipes. It's expensive, a lot of maintenance required. So they're going to compromise. They're actually going to compromise a lot. So they're going to compromise to 1 atmosphere of pressure, 1 ATM. So to summarize, we're going to have a temperature of 400 to 450 degrees Celsius, and we're going to have a atmosphere or a pressure of 1 atmosphere. So it's going to give us a reasonably high rate and yield. Okay, the position of the equilibrium already lies far to the right. So very high pressures is going to have an unnecessarily high cost. There's no need to go above 1 atmosphere really.